Hello guys, welcome back to my channel Gamma Digamma, and million apologies for not making a video earlier to continue our streak of linear algebra, but I'm here finally after my exams. Okay, so in this video I'm going to talk about eigenvectors and eigenvalues. Debatably one of the most powerful ideas in linear algebra and in various other branches of mathematics. So let's get started. Now let me introduce the idea of eigenvalues and eigenvectors. Consider a system like this. A v vector is equal to lambda times v vector, where consider A to be a matrix and v is a vector. Well, if you have such a system, and this is a special type of system, this vector is called the eigenvector, and this lambda, which is a scalar, is called eigenvalue. Now this equation doesn't tell us much about what's going on, so let's consider a more geometric picture. Well, since A is a matrix, you can consider it a linear transformation. Well, you can represent linear transformations as matrices on a well-defined vector space. So a linear transformation geometrically, what it does is if you have a vector in the input space, in this case it's v, what it does is when we apply this linear transformation, it basically rotates it or scales it up and down, or does both simultaneously, so that we have this final resulting vector that I've denoted in dots. Call this vector the linear transformation matrix applied on the original vector itself. Okay, now if we were to analyze this equation, what this equation is telling us is that if you take a vector, in this case it's v, and you basically apply linear transformation matrix on it, it just gets scaled up or down by a factor lambda. So what happens is, if you have a vector v, if you apply the matrix, instead of rotating it or completely changing the direction, in this case the direction is going to remain same, except it's just going to get scaled by a factor of lambda. So after transformation, you're going to get something like this, lambda times the original vector v, and that's what you get after applying the linear transformation matrix A on the original vector. It gets scaled, it doesn't change direction, it doesn't get rotated, it just gets scaled. So, and if you think about the identity matrix and what an identity matrix does to any arbitrary vector, consider the 3x3 identity matrix and an arbitrary vector, I don't know, call it W. What it does, it just returns W. So geometrically what happens is, you have a W vector here, you apply this linear transformation matrix, which is the identity. What it does is returns W, but scaled by a factor of 1. So it's similar to this example over here with the A times v vector is equal to lambda times v vector, except the lambda in this case is 1. So you can say that a system like this is basically finding vectors. Let me write this down properly. in a system like this, we're finding vectors for which the linear transformation A, denoted by A matrix, acts like the identity. I mean, not exactly the identity, but similar to the identity, because this lambda factor is not necessarily 1. It can be any. It can be negative 2. We can flip the direction and have a negative lambda as well. So that's why this term eigen in German means its own or self. So eigenvector is basically this linear transformation's own vector, and this scalar is like the linear transformation's own scalar, because that linear transformation for this vector is acting similar like an identity. It's just scaling it. It's not changing direction. We can think of the identity as not changing the direction. That's what this matrix A is doing for this vector V. It's not changing direction, it's just scaling it by a factor lambda. And this seems like a pretty trivial thing. It's like a basic exercise, but trust me, the applications of this are far reaching, and it's extremely powerful what this stuff can do. Okay, now let's try to calculate eigenvectors and eigenvalues the traditional way first. See you on the fresh page. Okay, so this is the equation that we actually started with. Now let's just do a bit of transposition. Now let's factorize out this, not factorize out, but apply it to a common term of A minus lambda times I. Remember, lambda is a scalar. If we basically plug out V from the entire term, we can't just leave lambda as it is, because otherwise we'll just have like a matrix subtracted from it a scalar. So that clearly doesn't make any sense. So to make this lambda into a matrix, we need the identity. And you can see if you apply V on this entire term using the distributive property, you get this expression back. So it's correct, whatever we've done. Now think about this system. This system is like A prime x vector is equal to 0. It's like that kind of system. This is like finding the null space of A prime. A prime in this case is A minus lambda I. Now we know one thing, that the null space being a vector space always has the 0 vector as the trivial element. It always has this. And we don't care about the trivialities here, because the trivial element would imply that V is 0. If V is 0, it doesn't matter what A minus lambda I is, we're gonna get 0 irrespectively. So we don't bother with this. This is like the trivial case. Let's worry about the non-trivial cases. When we know one thing, that when the columns of A minus lambda I, which is A prime, are linearly independent, that's when the null space, that's only when the null space includes the trivial case. But if the columns are linearly dependent, then we get some non-triviality in the null space. So we need to focus on this. We need to focus on basically having linearly dependent columns, or what we get when we have linearly dependent columns. Because then we can modify V according to what linear combinations of columns there are and get a non-trivial element in the null space. Now, what does linear dependence mean in terms of matrices? It means that when we row reduce the matrix A minus lambda I, we should have some free columns. At least one free column should be there. Otherwise, if we get identity on row reduction, it's the linearly independent case, and that's not helpful at all. That doesn't give much information. And what happens when columns are free? Well, I for one know that A minus lambda I will not be invertible. To be invertible, the matrix should row reduce to the identity completely. And what happens when you have non-invertible matrices? I mean, this, I didn't cover determinants, but this is a sort of step up. It means that the determinant of A minus lambda I is 0, or this A minus lambda I is a singular matrix. So in order to make sense or try to figure out lambdas and v's for this system, at least, we need to basically consider that the determinant of A minus lambda I is 0. Otherwise, if we didn't consider this, then we would just end up with the trivial case and won't have much information. This is the assumption we make if we want to find the non-trivial cases. Okay. I hope this part is clear to you guys. Now let's actually do this for a numerical example. Consider the matrix A to be -2, 12, 1, -3. Find the eigenvalues and eigenvectors. So we start with this to basically look at the non-trivial cases. So the determinant of A minus lambda I, if you do everything, if you do all the subtraction properly, you're going to get -2 negative lambda, 1, 12, -3 negative lambda. And now taking a determinant of a 2x2 matrix is child's play, honestly. And we need this to be equal to 0. So 2 plus lambda, 3 plus lambda, minus 12 is equal to 0. We have lambda squared plus 5 lambda minus 6 is equal to 0. And this equation, in terms of lambda or possible eigenvalues, is called the characteristic equation for matrix A. Just fancy terminology. Okay, we can easily factorize this out. Lambda minus 1, lambda plus 6 is equal to 0, which means lambda has two possible values, 1 and -6. Okay, fine, excellent, we got lambda. Now what? Now consider this equation that we had. Consider this equation, the starred one. A minus lambda I times the respective eigenvector v is equal to 0 vector. Well, now consider the case where lambda is 1. Then we have A minus 1 times identity is identity times, call this v1, is equal to the 0 vector. Now this system is precisely the system Ax is equal to 0. And how do you solve such systems? If you remember my first or second video on linear algebra, we row reduce. So A minus I is going to be this matrix, -3, 12, 1, -4. applied to vector v1 should give you the 0 vector. Now let's write the augmented matrix. I mean, I would have put this last 0 0 0, but I don't need that because zeros don't change on the performing elementary row operations. Okay, I have to basically row reduce this. Okay, so I'm gonna just skip some steps. We get 1 0, negative 1/3 and 0. Now v1 is naturally one-third and 1. Because if you apply this to this row reduced matrix, you're definitely going to get the null vector. And in fact, you could have taken any combination of these guys. You could have taken 2 times of this guy and like 2/3 of this guy. Basically any scalar multiple of v1 would work here, because all of those guys would solve this system of equations. So just take any linear combination of the basic null vector that you get, basic vector of the null space that you get for lambda is equal to 1. And now we have to solve for the second lambda value, which is -6. So for lambda equals -6, we have to row reduce 4, 12, 1 and 3, which on row reduction becomes 1 0, 1/4 0. And again for the second eigenvalue, now v2, linear combination of these is -1/4 and 1, and we could have taken any scalar multiple of this. We know our 2 eigenvectors corresponding to our 2 eigenvalues. Fine. Now let me just introduce this one idea. Why not change to eigenbases? A basis where v1 and v2 are the basis vectors. Basis where v1 and v2 are basis vectors. And we are going to change the basis of matrix A. And if you remember the formula for expressing a matrix in a new basis, it's going to be D, which is A in matrix in the eigenbasis, is equal to P inverse A P, where P is the transition matrix. And the transition, P is going to have columns v1 and v2. If you remember, if you watch my video on changing basis, you'll know that the columns are the basis vector of the new basis of in case of the transition matrix. And I'm just directly going to calculate P inverse. So finally D just becomes 12/7, 1 -1, 1/4 1/3. A was -2 12, 1 -3, 1/3 1, -1/4 1. If you multiply out everything, what you simply get is 1 0 0 -6. That's D. And if you notice closely, 1 is the eigenvalue corresponding to this first column of the transition matrix, corresponding to the first eigenvector, and -6, the second diagonal element, corresponds to the second eigenvector. And we can generalize this. Now the proof of the generalization is a little more advanced, so I'm just gonna extrapolate the result, so it's without losing generality. We can say that D is equal to P inverse AP, and D is just basically lambda 1 to lambda n, for example. And P is then going to be V1, the first eigenvector, second eigenvector for second column, last eigenvector for last column. And then P inverse is just the inverse of that. And then A can be expressed as PD P inverse. This D is always going to be diagonal, by the way. And this is the main equation that we need to be concerned about. This is the most powerful result of eigenvalues, the idea of eigenvalues, because in this way we can write an arbitrary matrix as a diagonal matrix. This process is called diagonalization. And why is this so useful is because if you try to calculate higher powers of A, say A squared, we have PD P inverse times PD P inverse. Now notice these consecutive terms cancel off. We have P D squared P inverse. And the best part about these diagonal matrices is that if you raise them to a power, the diagonal elements just get raised to that power. So in this case, we have lambda squared, everywhere else is a 0, lambda n squared P inverse. So, and you can do this for higher powers too. So a to the n will be P d to the n P inverse. And the best part about these diagonal matrices is that they are the closest to numbers, to scalar numbers, because if you take the inverse of a diagonal matrix, it's just going to be the multiplicative inverse of each of its diagonal elements. And in a similar way, you can basically raise e to the power of a matrix A, because then you're just gonna get e raised to each eigenvalue. Because since we know this holds true for powers, we can just use the Taylor series for the exponential function and get this result. And similar thing applies for sines, cosines, even natural logs of matrices. You can't beat this. I mean, you're finding natural log of matrices. It absolutely doesn't make sense, but on the other hand, with this application, it certainly does. Okay, so this was the traditional method of calculating eigenvalues and eigenvectors. This is what you're going to find in, I think, 98% of all videos on YouTube. Now, I would like to show you a little unconventional method, but it is pretty powerful in terms of computation, because I think about it this way. Calculating determinants is okay for 2x2 matrices, but 3x3 matrices, 4x4, higher dimension, it's a pain. It's a real pain. And more importantly than that, it's solving this polynomial too, finding roots of this polynomial. And sometimes it just doesn't factorize out. Sometimes you get irrational eigenvalues, sometimes even complex eigenvalues. If you take the traditional rotation matrix, rotation by angle theta in the xy plane, the eigenvalues of this guy are complex, imaginary actually, purely imaginary. So it just gets complicated. Then you need complex analysis and tools like that. Then you're going to expand the idea of exponentiation by Taylor series to exponentiation by Laurent series and stuff like that. And it's a pretty vast theory. So I would like to just show you an unconventional method that does not require you to calculate determinants. Instead, it just relies on your row reduction skills, because frankly today's computers are champions of row reductions. They're doing it so right now. I mean, in fact, when I put to edit this video out later, my computer will be performing millions of row reductions. So it's pretty easy to perform row reductions because inverses aren't an issue. This P inverse can be calculated using row reductions, but this determinant, we need to eliminate that whenever we can, wherever we can. So see you on the next page for a different approach. Okay, fine. Let's consider the matrix A, which is a 3 by 3 matrix now. 1, 1, negative 2, 0, 0, 2, negative 1, 0, 1. Fair enough. Now I have this crazy idea of expressing this entire system, or A to the power of the order of this matrix, some coefficient, call it A1 of the identity, plus A2 times the lower power A squared, plus A3, sorry, just A, and A3 times A squared. I have this crazy idea, but then I say, these are just matrices. I mean, it's harder to like perform row reduction or even solve system of equation with matrices. So I just multiply a standard basis vector, call it E1, on the entire system. So I just have A1 E1 plus A2 A E1 plus A3 A squared E1. Okay. And to basically get this, I need to have basically E1 A E1 A squared E1, and these coefficients A1 A2 A3. All I try to do essentially over here in this step is I want to express A cubed times this arbitrary basis vector as a linear combination of these guys, lower powers of A. And since these guys are vectors, this guy over here on the very left hand side will become a matrix, and this, we want that to be equal to A cubed times E1, which is a vector. So our system is essentially like A prime X is equal to B, and therefore we need to perform row reduction if we want to solve this system of equations. Row reduction on an augmented matrix this time, because this B is a non-zero vector. So to construct an A prime matrix, we need E1. Well, E1 is just standard basis vector 1 0 0. AE1, if you basically multiply out with this guy, you just get the first column of A. 1 1 negative 2. And if you meticulously calculate A squared, and then you take the first column of A squared, you're essentially gonna get 3 1 negative 2. Now let's construct a matrix out of them. We basically have, well first let's calculate A cube E1 2, because we need that in the augmented matrix. If you meticulously do that too, 5 3 negative 6. Now when we construct a matrix out of them, an augmented matrix for this system, because we want to solve for a1, a2 and a3, we get 1 0 0, 1 1 negative 2, 3 negative 1, so it's positive 1 negative 2, and 5 3 negative 6. This is the a cube part. This is the e1, this is a e1, a squared e1, and this is a cube e1 in augmented matrix for this system. Now simply row reduction gives us 1 0 0, 0 1 0, 2 1 0, augmented with 2 3 0. Well, if you just consider the original matrix A prime, not the a cube e1 part, we get this system of equations. We get a1 is equal to 2 minus 2 times a3. This is the variable corresponding to the free column, because the third column is a free column. a2 is 3 minus a3. The advantage of having systems defined like this is that now we can choose a3 to be anything, because that's the free variable corresponding to the third column, which is a free column. I don't know, let's take a3 to be 2, because now a1 gets to be negative 2, a2 gets to be 1. And now we can basically put these guys in our original a cube e1 equation. So a cube e1 is equal to negative 2 e1 plus a e1 plus 2 a squared e1, and this works for any value of a3 because a3 was the free variable. And this is almost like, you know, talking about choosing any linear combination of the original eigenvector of our system in the previous method. Any a3 value works. Now we can basically just write terms together. Minus 2a squared e1 minus a e1 plus 2e1 is equal to 0. Take e1 up front. A cube minus 2a squared minus a plus 2 times e1 is 0. Vector. These are all over vectors. Now we know that e1 is not 0. So the only way this thing could be 0 is if this guy is 0 itself. Because what e1 does is basically just takes the first column of this guy. And if e1 is not 0, then which means the first column of this guy must be 0. Or you can consider it this way. Let's not talk about vectors, let's talk about matrices. So you just ignore e1 because the 0 vector is 0 vector dotted with e1. So basically ignore e1 from both sides. Again, this is a heuristic approach, but whatever, it works. This is like the zero matrix, the null matrix now. And now let's multiply both sides by an arbitrary vector v. We're going to get a cube v, and if v is an eigenvector, a times v is going to be lambda v. Similarly, a times a v is going to be lambda times a v, which is a squared v is going to equal to lambda squared v. Similarly, for a cubed v, it's going to be equal to lambda cubed v. And if this v is an eigenvector, all these things hold true, and then a cube v is going to be lambda cubed minus 2 lambda squared minus lambda plus just 2 in this case v. I mean, all I did was I got lambda cubed v and then basically took v outside again. Now since v is not 0, because we don't want any non-trivial cases for our eigenvector, that means lambda cubed minus 2 lambda squared minus lambda plus 2 is equal to 0, and this indeed is our characteristic equation that we get. And you can check this if you can try to solve this problem using the first traditional method. You'll end up with the same characteristic equation. And the best part is, look at how these lambdas and a's are interchangeable. The fact that these are interchangeable is basically encompassed in a theorem that's called the Cayley-Hamilton theorem. And what I've done here is a very, very heuristic informal proof of the same. And again, we can factorize this out. We have to factorize this out. Lambda minus 2, lambda minus 1, lambda plus 1 is equal to 0. Eigenvalues are lambda equals positive 2, positive 1, negative 1. Yeah, 3 eigenvalues. Okay. Now let's actually try to solve for the eigenvectors. Now for the eigenvectors, the approach is going to be a little different, because the way we factorize out with these lambdas, we can interchange them with these a's. You can call that a consequence of the Cayley-Hamilton theorem, but instead of just having a 2, we need to have 2 times identity now, because A is a matrix. A minus I, A plus I. Is equal to 0. Let's multiply E1 on both sides, so you get 0 vector here. Now we can simply factorize out A plus I. We have A minus I, A minus 2I, and by the way, this product is pretty commutative with E1 acting on it. Now if we call this system V1, we have A plus I times V1 is equal to the 0 vector. This is almost like A minus lambda I times vector V is equal to 0, except if we take lambda equals negative 1, and this eigenvalue was indeed what was one of the eigenvalues that we got. So this case is for lambda equals negative 1, which means V1 is the eigenvector corresponding to lambda equals negative 1. And what is V1? This bracketed guy, A minus I, A minus 2I, E1. That is your V1. So just find this out. I mean, this is just a matrix multiplication. It's probably a little more convenient than doing those row operations, row reductions for finding E1, for finding V1, sorry. And I'm just going to skip to the, I'm going to, just this product basically is 2, negative 2, 4, negative 2, 2, negative 4, 1, negative 1, 2, 1, 0, 0. So just take the first column and you have 2, negative 2, 4 as the first eigenvector corresponding to lambda equals negative 1. Now, notice this, all these columns are linearly independent. I mean, you could have just picked any column and it would have been an acceptable eigenvector, because as I said, you can take any scalar multiple of v1. Now this idea is, however, more relevant for the second eigenvector calculation that we're going to do, because it seems that we made a mistake somewhere, or it's not helpful at all, but it is. So consider lambda equals 1. Then we can factorize out lambda minus a minus I and take bracket these other terms out. And we can call this our v2, the second eigenvector. So if you just do this multiplication, you are gonna get 0, 0, 0, negative 2, negative 2, 0, negative 1, negative 1, 0, 1, 0, 0. Now this means just take the first column, which is 0, 0, 0. Now the issue here is that we are getting a trivial eigenvector. This is a trivial case, and we don't want to work with those. So just choose the next column, because what happened is that in this matrix, the other columns were like multiples of any one column. So 0 is theoretically a multiple of both of these guys. You just multiply both sides with the scalar 0, and because null spaces are subspaces, they need to contain the 0 element. That's why this is actually an acceptable solution to this problem, but it doesn't help us, especially when we're trying to diagonalize and then find the inverse later. This doesn't help us much and can't help us diagonalize stuff later, because the inverse can be calculated later. So just choose any other column, because there's nothing special about this e1, this first basis vector. You could have had e2, the second basis vector, 0, 1, 0. Then you would have gotten the second column. And hell with the basis vectors. We could have even taken this random arbitrary vector 2, 1, 0, and we would have still ended up with an acceptable value for the eigenvector for lambda equals 1. So just choose it. So call this solution extraneous or irrelevant or insignificant or whatever, and just choose any other column and just be done with it. You're gonna get negative 1, negative 1, 0. You can take any linear combination of that. So just multiply that with negative 1, you get 1, 1, 0, which is an acceptable eigenvector itself. Okay, now for lambda equals 2, our equation for the eigenvector 3 is a minus I, a plus I times the identity vector, the basis vector. And after computation, we end up with 2, negative 2, 1, negative 2. And now let's just construct A as PDP inverse according to some observations we made in the last part. We have negative 12 up front because of the inverse, 2, negative 2, 4, 1, 1, 0, 2, 1, negative 2. Now D is, 2, negative 2, 4 was the eigenvector corresponding to 1, lambda equals 1. So 1, 0, 0. And for the second diagonal entry, 1, 1, 0 corresponding to let's see, let's check again. This was negative, the first was negative 1. This guy will be 1 then. And the last guy will be 2. And my P inverse turned out to be, I took the negative 12 outside, negative 2, 0, negative 4, 2, negative 12, 4, negative 1, negative 6, 4. And look how you can decompose A into some correction matrices, if you want to talk about it, and this diagonal matrix. This is what or the professors who taught me called decoupling the system, because you are reducing a complicated matrix, an arbitrary matrix, into a diagonal matrix, which is the most easiest matrix to work with in terms of multiplication, inverses, powers, and these bunch of correction factors. These factors ensure that A is not equal to this diagonal matrix. Otherwise, it would just, there was no need to diagonalize this anyway if A was already diagonal. And you can think about that these matrices tell how to combine these fundamental diagonal elements in order to generate an arbitrary matrix A. So this is like at the root of matrix A, if you wanna, not like the mathematical square root, but like the fundamental structure of A, if you want to think about it that way. And this is what has millions of applications. And with this unconventional method, I hope you found this helpful. It's slightly easier to calculate because look at it this way: we just completely surpassed the determinant and also informally proved this Cayley-Hamilton theorem, which is like a big theorem, which is helpful for solving differential equations and a bunch of other crazy stuff. Now this video has already been long, but I do apologize, but like I need to discuss the applications because this is so powerful. It gives me goosebumps every time I think about it. Now the first application of eigenvalues and eigenvectors. The first application is to solve differential equations, or with any type of differential equations. There's a way of categorizing systems of differential equations based on their eigenvalues and even degeneracies. If the eigenvalue is repeated when you try to factorize out the characteristic equation, that means two different eigenvectors have the same eigenvalue and there's a degeneracy in the system. So for solving differential equations, it's really helpful to know the nature of systems. I'm probably going to make a video of where I solve a system and know the fundamental modes of vibration or oscillation of that system, combined springs and stuff like that, especially differential equations with the exponential functions involved in them. Second is, I would say, Google's famous ranking algorithm, the way it ranks web pages, is based on one of a theorem on eigenvalues and eigenvectors called the Perron-Frobenius theorem, which guarantees that a positive matrix will have a maximum positive eigenvalue, and then using that you can basically generate an algorithm of differences in ranking. Third is, facial recognitions with a similar principle as application number 2, but this actually uses something that's called the spectral theorem, tries to construct an orthogonal basis using eigenvectors, eigenvalues of a system, and assuming you have one face put in, you construct a face that is the most distinct to it, and then construct a system of a third face which is completely different to the first two faces. So it's a sort of recurring inner product sort of algorithm that's happening, and some researchers even showed that the brain is actually doing this when we try to distinguish between different people. And then I would talk about many of physics, actually. Quantum mechanics. And the way my professor put this is, quantum mechanics is just spectral theorem in Hilbert space. That's all of quantum mechanics, because you all have operators, which are the physics term for matrices. You have states, which is the physics term for vectors, and you have eigenvalues, let's say eigenstates, eigenvectors, eigenvalues, or you can say observables. And all you have to do is, say you have this energy operator acting on a wave function psi. You basically, let me put it in a better way. You have this Hamiltonian operator, which is like the total energy of a system. You apply that on some given eigenstate. You get the corresponding eigenvalue, which is the energy of the system times this eigenstate. So this becomes an eigenvalue problem basically. And another example basically, or perspective, is rotation matrix. If you have a rotation matrix, some arbitrary numbers, non-diagonal, with some arbitrary entries everywhere, you can decompose this as PDP inverse, and D has some diagonal entries, just diagonal entries. And if you consider the diagonal entries, the diagonal positions to be the principal axes, say this is rotating in like, this rotation was in like n dimensional space or something like that. It had n degrees of freedom with respect to rotation. We can decompose the system in and basically quantify what value of rotation with respect to that principal axis we have, given by these eigenvalues, and basically decouple the system. In this case, it's right to use the term decouple the system and understand what's going on. And this is particularly useful because the moment of inertia is actually a tensor, which has basically Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz. And if we can decouple this system to basically just have Ixs, Iyy, Izz, not exactly the same coefficients, but just these diagonal entries, and these combinations of basis vectors is basically the principal axis for a three-dimensional system, three-dimensional rotation. So this is truly decoupling the system, and it's really, really useful when you want to do some rotational mechanics and analysis of that sort. So these are just a bunch of applications. This is really powerful. I mean the concepts of PDEs, the stability of PDEs, partial differential equations, rely on eigenvectors and eigenvalues of a system. Quadratic forms in differential manifolds and differential geometry. The idea of a signature and degeneracy and like classification of the system is done with eigenvalues. The Hessian matrix, or to know where we have a maxima, minima in multivariable calculus, or even a saddle point, is done with the positive definite eigenvalues, positive negative definite eigenvalues. Is basically like we have the discriminant for the quadratic equation. That's how eigenvalues are for systems like these PDEs, quadratic forms. I mean, that's still the tip of the iceberg, I think. It's extremely, extremely important. I'm glad you stuck as far as this video, because I think this covers all of this video series I've made in linear algebra covers, I think, all of the functional concepts you need to survive in a physics or math course at university. So yeah, I hope you enjoyed. Please like, share, and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Diagram in the math community. And in the meantime, stay home, stay safe, and peace out.